Hello guys, and welcome to my YouTube channel. In this video we are going to look at how solar panels are made, starting from raw quartz sand and ending with a complete photovoltaic module that can generate clean electricity. The full journey begins with quartz or silica sand, which is the raw source of silicon. This material is converted into metallurgical silicon, then purified into high purity polysilicon. After that, the polysilicon is melted and grown into ingots. These ingots are sliced into very thin wafers, and the wafers are processed into solar cells. Once the cells are ready, they are connected together, laminated between protective layers, framed, tested, and finally turned into a finished solar panel. Inside one panel, you will find silicon cells, tempered glass, encapsulant films such as EVA or POE, copper ribbons, silver contacts, aluminum framing, a backsheet or rear glass, a junction box, bypass diodes, and output cables. So a solar panel may look simple from the outside, but inside it is a carefully engineered stack of materials designed to survive heat, rain, wind, ultraviolet light, and mechanical stress for many years. The first important thing to understand is the material structure of a solar panel. The active part of the panel is the silicon solar cell. This is the part that actually converts sunlight into electrical energy. But the cell alone is extremely fragile, so it must be protected by several layers. At the front there is low iron tempered glass. This glass is used because it allows a high amount of sunlight to pass through, while also protecting the cells from impact, weather, and mechanical damage. Below the glass we have an encapsulant layer, usually EVA or POE. This polymer film bonds the cells to the glass and helps protect them from moisture and ultraviolet exposure. The solar cells are connected together using copper interconnect ribbons. These ribbons carry electrical current between cells. On the surface of each cell, silver contacts collect the current generated by the silicon. At the back, there is another encapsulant layer and then either a polymer backsheet or rear glass. The backsheet provides insulation and weather protection. In some newer or bifacial modules, rear glass is used instead, which can improve durability and allow light to enter from the backside. Finally, the panel includes an aluminum frame for mechanical strength, a junction box for electrical connections, bypass diodes for protection during shading, sealants for weatherproofing, and output cables to deliver DC power to the system. So when we talk about a solar panel, we are not talking about only silicon. We are talking about a complete engineered module made from glass, polymers, metals, semiconductors, and protection components. The manufacturing process starts with quartz or silica sand. Chemically, this raw material is mostly silicon dioxide, written as SiO2. Silicon dioxide is very common in nature, but it is not directly usable as a solar cell material. To extract silicon, quartz is mixed with a carbon source such as coal, coke, or another carbon-rich material. This mixture is heated inside an electric arc furnace at extremely high temperatures. Inside the furnace, carbon reacts with oxygen from the silicon dioxide. This reduction process separates silicon from oxygen. The result is metallurgical grade silicon. This material is usually around 98% pure, which may sound very pure, but for solar cells it is still not pure enough. Solar cells need extremely clean silicon, because even tiny amounts of unwanted impurities can reduce efficiency and long-term reliability. During this furnace process, carbon monoxide gas is also produced as a byproduct. So, in simple terms, the first step is quartz plus carbon plus very high heat, producing metallurgical silicon. This is the foundation material, but it still needs much more purification before it can become part of a solar panel. After metallurgical silicon is produced, the next step is purification. This is where ordinary industrial silicon is converted into solar-grade polysilicon. First, the metallurgical silicon is crushed into smaller pieces. Then it reacts with hydrogen chloride gas at high temperature. This reaction produces chlorosilane compounds, especially trichlorosilane. Trichlorosilane is useful because it can be purified more easily than solid silicon. Next, the gas goes through a distillation process. Distillation separates unwanted impurities and allows manufacturers to reach extremely high purity levels. This is important because solar cells require silicon, with impurity levels reduced to the parts per billion range. One common purification method is the Siemens process. In this method, purified trichlorosilane gas enters a reactor containing heated silicon rods. The gas decomposes on the hot rods, and ultra-pure silicon deposits onto them. Over time, the rods grow into thick, high-purity polysilicon structures. There's also another method called the fluidized bed reactor process, where polysilicon can be produced as small granules instead of large rods. Both methods aim for the same goal, to create silicon clean enough for efficient and reliable solar cells. This step is one of the most energy-intensive and technically demanding parts of solar panel manufacturing. Once high-purity polysilicon is ready, it is melted and formed into solid crystal structures called ingots. For monocrystalline solar panels, the most common method is crystal pulling. A small seed crystal is dipped into molten silicon and slowly pulled upward while rotating. As it rises, silicon atoms arrange themselves in the same crystal direction as the seed. This creates a single crystal ingot. Monocrystalline silicon has a very ordered structure, which helps electrons move more efficiently. That is why monocrystalline panels usually have higher efficiency. For multicrystalline silicon, the process is different. The molten silicon is poured into a mold and cooled in a controlled way. Instead of forming one continuous crystal, it forms many crystal grains. This is usually cheaper to produce, but the grain boundaries can reduce electrical performance. After the ingots or blocks are formed, they are shaped and squared to the correct dimensions. Then they are sliced into very thin wafers, using diamond wire saws. These wafers are typically around 160 to 180 micrometers thick. During slicing, some silicon is lost as fine sawdust. This is called kerf loss. Because silicon purification is expensive, reducing kerf loss is very important for lowering manufacturing cost. At the end of this step, the result is a stack of thin silicon wafers ready for solar cell processing. Now the silicon wafer must be turned into an actual solar cell. The first stage is cleaning and saw damage removal. Wafer slicing leaves microscopic damage on the surface, so chemical cleaning and etching are used to remove damaged material and contamination. Next comes surface texturing. The wafer surface is shaped into tiny pyramid-like structures. These microscopic pyramids reduce reflection and help trap more light inside the silicon. A flat, shiny wafer reflects more light, but a textured wafer absorbs more. After that, the wafer is doped to create a PN junction. Doping means adding very small amounts of selected atoms, such as phosphorus or boron, to change the electrical behavior of the silicon. One region becomes N-type, which is electron-rich, and another region becomes P-type, which is hole-rich. At the boundary between these two regions, an electric field forms. This electric field is extremely important because it separates the electrons and holes created when sunlight hits the cell. Without this junction, the cell would not generate useful voltage. Then edge isolation is performed to prevent unwanted current leakage around the wafer edges. Finally, passivation and anti-reflection coatings are added. Materials such as silicon nitride and aluminum oxide help reduce surface recombination and improve light absorption. At this stage, the wafer is no longer just a piece of silicon. It has become the foundation of a working photovoltaic cell. After the wafer structure is prepared, the solar cell needs electrical contacts. These contacts collect the current generated inside the silicon and carry it out of the cell. The front side of the cell usually receives fine silver contact lines. These are often screen printed using silver paste. The silver lines must be conductive enough to collect current, but thin enough to avoid blocking too much sunlight. The rear side of the cell also receives a contact layer. Depending on the cell type, this may include aluminum, silver aluminum paste, or other metal structures. After printing, the cell goes through a firing furnace. This high-temperature process burns off organic materials from the paste and bonds the metal contacts to the silicon. The firing step must be carefully controlled. If the temperature is wrong, the contacts may become weak, or the cell efficiency may drop. Once metallization is complete, the cell is tested. Manufacturers measure the current voltage curve, open circuit voltage, short circuit current, fill factor, and maximum power. Cells are also inspected for cracks, broken fingers, and defects using visual inspection and electroluminescence imaging. Finally, the cells are sorted by power and quality. This sorting is important because cells connected in the same module should have similar electrical performance. If one weak cell is placed in a string, it can limit the output of the whole panel. Now that the solar cells are finished, they must be assembled into a complete module. First, cells are connected together using copper ribbons. This is called tabbing and stringing. The cells are usually connected in series. so the voltage of each cell adds up to create the required module voltage. Next, the cell strings are aligned into the final panel layout. After alignment, the module layers are stacked in the correct order. From the front to the back, the stack usually includes tempered glass, EVA or POE encapsulant, solar cell strings, another encapsulant layer, and a backsheet or rear glass. The order of these layers is extremely important. The glass protects the panel from impact and weather. The encapsulant bonds the structure together and seals the cells against moisture. The backsheet or rear glass provides insulation and long-term protection. After the stack is prepared, it goes into a vacuum laminator. The laminator removes trapped air, heats the encapsulant, and bonds all layers into one sealed structure. This is one of the most critical steps for long-term reliability, because poor lamination can lead to bubbles, delamination, moisture ingress, or cell damage. After lamination, excess material around the edges is trimmed. Then the panel is framed with aluminum, making it stronger and easier to mount. At this point, the fragile solar cell strings have become a durable photovoltaic module. A finished solar panel has several important components working together. The aluminum frame gives the module mechanical strength and protects the edges. The front glass protects the solar cells from rain, dust, hail, wind, and impact while allowing sunlight to pass through. Under the glass, the solar cells convert light into electricity. The encapsulant layers hold the cells in place and protect them from moisture and vibration. Behind the cells, the backsheet or rear glass provides insulation and environmental protection. On the rear side, the junction box contains the electrical connections. This is where the internal cell strings connect to the external output cables. The output cables carry DC power from the solar panel to the inverter or charge controller. Inside or near the junction box, bypass diodes are used to reduce hotspot problems. When part of a panel is shaded, the affected cells can become a resistance path and heat up. Bypass diodes allow current to flow around shaded sections, reducing power loss and protecting the module. Many modern panels also use half-cut cells. By cutting cells into smaller sections, current per cell section is reduced, which lowers resistive losses and can improve performance under partial shading. So the final panel is not only a collection of solar cells, it is a complete electrical and mechanical system designed for outdoor operation. Before a solar panel is shipped, it must pass several quality and safety tests. First, visual inspection checks the appearance, alignment, labels, glass, frame, and general workmanship. Then electroluminescence testing is used to detect hidden defects such as micro cracks, broken cells, and soldering problems. These defects may not be visible to the human eye, but they can reduce long-term performance. The panel also goes through a flash IV power test. In this test, a solar simulator flashes light onto the module, and the current voltage curve is measured. This gives the rated power, voltage, current, and efficiency under standard test conditions. Electrical safety tests are also required. An insulation or high pot test applies high voltage to confirm that the panel is properly insulated and safe to use. A wet leakage test checks whether moisture can cause electrical leakage. Mechanical load testing verifies that the panel can withstand wind and snow pressure. Thermal cycling exposes the module to repeated hot and cold temperature changes. Damp heat testing checks performance under high humidity and high temperature. Hail testing confirms that the glass and module structure can survive impact. These tests are essential because solar panels are expected to work outdoors for 20 years or more. A panel must not only produce good power on day one, it must remain safe, stable, and reliable for decades. Most solar panels in the world today use crystalline silicon, but there are also thin film solar technologies. Thin film panels are made in a different way. Instead of slicing thick silicon ingots into wafers, manufacturers deposit very thin semiconductor layers directly onto glass, metal, or flexible substrates. One common thin film technology is cadmium telluride, or CDTE. It performs well in large utility-scale projects and can be manufactured at relatively low cost. Another type is CIGS, which stands for copper indium gallium selenide. CIGS can offer good efficiency and can be made on lightweight or flexible surfaces. Amorphous silicon is another thin film option. It can be deposited at low temperatures and works well in low light, but its efficiency is usually lower than crystalline silicon. The thin film process usually starts with coated glass or a flexible substrate. Then semiconductor layers are deposited using methods such as sputtering or evaporation. Laser scribing divides the layers into individual cell sections and creates electrical isolation. After that, a back contact is added, protective layers are laminated, and the module is finished and tested. Thin film can be lighter or more flexible depending on the design, but crystalline silicon still dominates the market because of its high efficiency, mature manufacturing process, and strong long-term reliability. So the full solar panel journey can be summarized like this. Sand becomes silicon. Silicon becomes wafers. Wafers become cells. Cells become modules. And modules turn sunlight into clean electricity. Thanks for watching this video, guys. Please share, like, and comment below. Also subscribe to my YouTube channel for more videos.